Welcome back. So in this lecture, we will reach this very interesting technique called adaptive control. But before that, we will look at general challenges. It gives us a chance to actually summarize what we have done so far, right? And then we will get into basics of adaptive control. So the part one is going to be what's the basic problem a control designer faces, right? So anyway, we will assume, this is a standard assumption throughout the course, that somebody gave this ODE model, right? It's probably based on first principles or data or however they got ODE model is given. And it has an appropriate equilibrium that we want to control towards, and then it has right inputs and right outputs, right? And typically we may assume that every state can be controlled and measured, and there are sufficient number of input activators, right? Of course, one of the first things that we learned in the course is basically existence and uniqueness and things like that. And invariably, most of the time when we actually put a closed loop system, we want the solution to behave in such a way that we have unique solution globally and things like that. Rarely we have other possibilities. So in most of the time, I can't think of immediately any case where we don't want this particular property. So the models, the existence and uniqueness results we learned, are useful for that. But of course, whenever something like that does not work out, if the conditions that we learned in the first couple of weeks of these lectures, what do we have to do? The choice we have is actually understanding the physics and then basically see if the ODE model is actually consistent with physics, right? So otherwise we have to throw it away and then probably modify the solution, modify the ODE and things like that. Then we actually went into Lyapunov stability theory, and the biggest difficulty of, in one sense, basically we don't have a choice but to understand Lyapunov stability, because nonlinear system behavior, if you want to talk about some good behavior, then Lyapunov stability is one of the best things that we can think of, some kind of perturbation from an equilibrium, how it behaves after that. So, and then through this very intuitive idea of energy, we developed this theory of Lyapunov function. Lyapunov did, okay? And then, but unless we get this natural or physical energy for some particular system, suppose if it is a system developed through phenomenological models, for example, how drug spreads through the body and things like that, it has some understanding of physics, but it doesn't follow any physical principles the way we think of Newton's laws and things like that. In such a case, basically we may end up with guessing an energy rather than having it automatically coming from the system, right? But in some cases that's also very difficult, so in which case we typically rely on this linearization method, right? Linearization is a nice method. It's a local method. If you recall, basically it simply approximates the nonlinear system to a local system. And it has its limitations, because if there is a system that has essential nonlinearity, some kind of limit cycle behavior, or something like a cubic nonlinearity to start with, and you don't want to throw away that particular cubic nonlinearity, then we'll end up with difficulty. That's the standard approach. Most people take linearization, but sometimes we may want to force ourselves to go for nonlinear methods, and in which case we can actually try this sum of squares, which I haven't shown you any examples and things like that, but it's based on the semi-definite programming of polynomial systems, for example. So there's a nice way of checking for positive definite Lyapunov functions and positive definite negative definite v dots of all polynomials of a certain degree and things like that, and then it provides a nice method, right? What are the other alternatives if these things, these things are brute force searching for Lyapunov functions through these approximation methods, typically that give you local stability and things like that. Another way of doing it is, okay, maybe take this nonlinear problem, divide into some linear part and then nonlinear part, or both nonlinear, and then the nonlinear part is much more well behaved, as we have seen. Somehow perhaps it has a dissipativity property, and then we can think of it as a feedback interconnection of two dissipative systems, and that's what absolute stability and robust stability problems do, right? Robust stability is typically discussed in the case of linear systems, and whereas absolute stability is its extension to nonlinear systems, right? And there are other techniques, wonderful techniques based on some deep theory coming from differential geometry. We'll see things like Lie groups, Lie derivatives, and things like that. And there is a general methods that allow us to basically, through feedback, we can make the system, render the system linear, right? So you may have a complicated nonlinear system. By transforming its coordinates to a particular, special coordinates, we can actually have the system in a very specific form, cascaded form. And once we have that cascaded form, we can actually linearize the system. That is basically, put the feedback, and then through feedback, the system becomes nonlinear. As much as it is wonderful theoretically, again, it also suffers from many difficulties in terms of showing a lot of these things computationally. Again, sum of squares and things like that may become useful there for certain classes of systems. And of course, we saw in the case of robust stability problem, though it was linear, model parameters, if they are not accurately known, how to deal with that aspect. But sometimes what happens is basically, these model parameters are not known to be approximate, but we know that they're there. It's just that we cannot measure that, or it may take too much time to measure and things like that, right? Going back to example of drug injection or something like that, every time if we want to inject something into your blood and then you want to guess the model and then estimate the parameters and things like that, it's not going to work out. It's better actually to figure out a technique where I know that there is a parameter, but I just don't know how to estimate it. Perhaps the input-output properties are good enough to actually somehow control this particular system. So we have anything to do with model parameters and things like that, robust stability and dissipated theory, and then of course adaptive control technique, which is what is the focus of this particular lecture. There are still other aspects that we will probably consider later in the course as external noise and disturbance, right? So how do we deal with it? Again, in fact, the answer is quite simple. Dissipated theory comes into picture. In fact, the specific notion of non-expansivity comes. All these things do not consider anything about basically optimization, right? And then that's a big thing for us, because we not only want to design controllers that make the system stable, but we actually want to pick that controller that actually minimizes some kind of performance or maximize some performance, right? Depending on how you define, minimize the cost and maximize the performance, right? So, and then there will be many questions, what kind of performance and things like that. And then we will see a couple of lectures later, this entire topic of optimal control, and followed by disturbance rejection and things like that. And anyway, our optimal control, I won't speak much more. There is something called calculus variance approach, and then as an extension to that, there is a very practical method called model predictive control. And one of the nice things about optimal control approach is some of the, this is a very general statement I'm making, it's not always true. Whenever we want to optimize something, that means we are kind of maximizing the utility of resources we have. We are in the brink of, I'm going to use the word very loosely, instability. That means basically trying to extract the maximum out of this particular system. So what's possible is slight perturbation from that maximum utilization of the resources. You can actually destroy the system. But some of the optimal control answers that we get out of the optimization happen to be stable in a certain way, robust in a certain way. And then we will discuss that in the topic of stability margins. And the last thing towards the end of this particular course, what we will hint at is basically all these things are nice and good if we have a good model, and then we have a way of finding Lyapunov stability and optimal controllers and whatnot. But in most cases, we won't even have such a model, or the model is too complicated, in which case we don't know what to do. So what can we do? Well, we only have access to some input-output data. We don't even have a notion of state, perhaps. And artificial neural networks have been used. It's what you keep hearing, the machine learning models for pretty much everything that we see in this world. And more importantly, these are called model-free approaches, and I have a certain hesitation in terms of calling them completely model-free, because I don't really think of any system that is totally model-free. And we will look at some of those details towards the end of this particular course. All right. So these are the challenges, and then we'll hopefully see some of the answers. But as you can see, each one of them is quite a complicated topic in itself, and then sometimes we go really into depth. Sometimes we may actually end up with giving some idea in terms of how to approach these problems. The techniques are introduced and not as a very general technique that you can use it in a computational fashion, but as an art that you actually applied somewhere else in probably slightly varying conditions and things. So pay attention to the details in terms of why each one of them work. So with that, this particular lecture is over. We'll come back and talk about part 2, where we discuss basics of adaptive control.